The heat is no longer behaving like summer. Across the United States, temperatures are rising beyond familiar limits. Nights are no longer cooling, and entire cities are starting to feel like they cannot breathe. What was once called a heat wave is now becoming something far more dangerous, more persistent, and harder to escape. This is not just extreme weather. This is a warning sign of a changing world, and what is unfolding now may be unlike anything America has seen before. If this is the kind of deep cinematic documentary watch to the end, remember to like the video, subscribe to the channel, and stay with the story. The planet turns steadily beneath the sun, its axis tilted so that one hemisphere leans closer into the light during part of the year. In this period, the northern hemisphere receives longer days and a higher angle of sunlight. The United States lies within these latitudes, where summer brings a persistent arc of daylight that stretches from early morning into late evening. Solar radiation, the energy that arrives from the sun, reaches the upper atmosphere and continues downward, interacting with air, clouds, and the surface below. Some of this energy reflects back into space, while much is absorbed, warming land and water. At the global scale, this process follows patterns that have remained consistent over long periods. The distribution of continents and oceans shapes how heat is stored and released. Land warms more quickly than water because it has a lower heat capacity, meaning it requires less energy to increase in temperature. Oceans absorb vast amounts of heat and release it slowly, moderating nearby climates. The interior of a large continent, however, responds more rapidly to changes in sunlight, especially during extended periods of clear skies. Across North America, the broad landmass stretches from subtropical zones in the south to cooler regions in the north. During summer, solar energy accumulates over this land. The angle of incoming sunlight increases the intensity of heating as rays strike the surface more directly rather than at a slanted angle. Days lengthen, allowing more time for energy to build. Each day adds to the heat stored in soil, vegetation, buildings, and paved surfaces. When nighttime arrives, some of this stored energy is released, but under certain conditions, not all of it escapes. The atmosphere above the continent plays a crucial role in how this energy behaves. At the outermost layer of the heatwave setting, large-scale atmospheric circulation governs the movement of air masses. Air moves in broad currents driven by differences in temperature and pressure across the globe. In summer, warm air tends to dominate over continental interiors. The circulation patterns can become stable, reducing the movement of air and limiting the exchange between regions. Observations indicate that during certain periods, these patterns slow and become more persistent. The jet stream, a high-altitude river of fast-moving air, can shift position or weaken in its flow. When it slows, it may form broad waves that remain in place for extended durations. These waves influence weather systems below, allowing some regions to remain under similar conditions for many days. In the case of a heat wave, this often means sustained warmth with little interruption. At the planetary boundary between space and atmosphere, incoming solar radiation interacts with gases such as nitrogen, oxygen, and trace components like carbon dioxide and water vapor. These gases allow most sunlight to pass through, reaching the surface. The surface then emits energy back upward in the form of infrared radiation, a longer wavelength of energy associated with heat. Certain gases absorb part of this outgoing energy and re-radiate it in multiple directions, including back toward the surface. This process contributes to the warming of the lower atmosphere. The balance between incoming solar energy and outgoing infrared energy determines the overall temperature of the planet. When more energy is retained than released, temperatures rise. Over long periods, small shifts in this balance can alter climate patterns. During a heat wave, this balance shifts locally and temporarily, with more energy accumulating in a specific region than can be dissipated. Across the United States, the early stage of a heat wave appears as a gradual increase in temperature over several days. Weather stations record daily highs that begin to exceed seasonal averages. Nights may remain warmer than usual, indicating that the accumulated heat is not fully dissipating after sunset. The air mass over the region becomes increasingly warm, setting the stage for further intensification. From a satellite perspective, the continent shows large expanses of clear skies. Clouds, which normally reflect sunlight and provide shade, are limited in these conditions. Without their presence, solar radiation reaches the surface with fewer obstacles. Land areas absorb this energy efficiently, particularly where vegetation is sparse or soil moisture is low. The surrounding oceans continue to play a role, though at this outer scale they act more as background moderators. Coastal regions may experience some influence from cooler marine air, but when large-scale atmospheric patterns favor continental heating, this moderating effect can be reduced. Inland regions, far from the stabilizing influence of water, become more susceptible to rapid temperature increases. At this stage, the heat wave is still defined by its broad, outer context. It exists as a regional imbalance in energy, shaped by the position of the sun, the tilt of the earth, and the arrangement of atmospheric circulation. It does not yet depend on local details such as soil condition or urban structure. Instead, it reflects a large-scale alignment of factors that allow heat to accumulate over a wide area. Measurements from weather balloons and satellites show warming throughout the lower layers of the atmosphere. Temperature profiles reveal that the air near the surface is becoming increasingly warm, while higher layers may also exhibit elevated temperatures. This vertical structure is important, as it influences how heat is distributed and whether it can rise and disperse or remain trapped. The process remains steady and continuous. Day after day, sunlight arrives, and more energy is absorbed than released. This system does not require sudden change to produce extreme conditions. Instead, it builds gradually, through persistence and accumulation. The outermost region of the heat wave, defined by planetary and continental factors, sets the foundation upon which all later developments depend. It remains uncertain in specific cases how long such a pattern will persist, as atmospheric circulation can shift in response to distant influences. However, when the alignment holds, the result is a sustained period of heat that extends across large parts of a continent. The United States, positioned within this summer framework, becomes one such region where energy accumulates under a stable sky. The scene remains expansive and quiet at this outer scale. There is no sudden boundary marking the start of the heat wave, only a gradual intensification across space and time. The sun continues its path across the sky, and the land beneath it continues to warm, establishing the conditions that will deepen as the focus moves inward. Above the heated continent, the summer atmosphere settles into a broad and layered mass of air that grows warmer through depth as the days pass. North America spans deserts, plains, forests, river valleys, mountains, and coasts. Yet from high above these varied surfaces, the atmosphere begins to behave as one connected system. Warmth does not remain only at the ground. It spreads upward through the lower part of the air column, creating an extended body of heat over the land. This is the continental atmosphere in its summer state, shaped by the balance between sunlight below and large-scale air motion above. Air over land responds quickly when the surface warms. During the day, the ground absorbs solar energy and transfers part of it to the air directly touching it. This transfer happens through conduction, which is the movement of heat through contact, and through convection, which is the rise of warmer, lighter air and the sinking of cooler, denser air. As the ground grows hot, the air near it becomes more buoyant and begins to move upward in slow and uneven currents. This motion mixes warmth through the lower atmosphere, creating a deeper warm layer over wide regions. Over the United States in summer, this warming often extends through much of the troposphere, the lowest major layer of the atmosphere where weather takes place. The troposphere contains most of the air's mass and nearly all of its water vapor. It is the region where clouds form, winds shift, and storms grow during a heat wave. The lower and middle parts of this layer often become warmer than average across a broad area. The warmth is not only a surface event, it is a deep atmospheric condition, extending well above the ground and making relief more difficult. The continental scale matters because the landmass itself helps sustain this change. As the central and western parts of North America heat under strong summer sunlight, the warmed surface feeds energy into the air above. That warmed air can expand horizontally and vertically, building a broad reservoir of heat. When winds from cooler regions are weak or displaced, there is little exchange to interrupt the warming. The atmosphere then becomes more uniform in its heat, especially across the interior. Meteorologists often describe this type of setup as a heat dome. The phrase refers to a large region of warm, sinking air associated with strong high pressure aloft. The name can suggest a solid cap, but in practice it is a broad three-dimensional structure in the atmosphere where air has been compressed and warmed. Compression happens when air descends. As it sinks into lower altitudes, the surrounding pressure increases. The air parcel is squeezed into a smaller volume, and its temperature rises even without receiving new heat from the sun during that descent. This is called adiabatic warming, a change in temperature caused by pressure change rather than direct heat transfer. Over a continent in summer, a persistent high-pressure region can create this descending motion across a vast area. The sinking air discourages vertical mixing beyond a certain depth, suppresses widespread cloud growth, and helps maintain stable conditions. At the same time, the surface below continues to receive strong sunlight. The result is a layered atmosphere in which warming occurs both from above, through sinking and compression, and from below, through heated land. These two processes reinforce one another. The air mass becomes increasingly self-consistent. Daytime heating strengthens the warmth near the ground, while the high-pressure pattern supports warmer conditions higher up. This reduces the ability of surface heat to escape upward freely. The atmosphere is still in motion, but its motion favors persistence rather than change. Instead of frequent fronts moving across the continent and replacing one air mass with another, the same warm body of air remains in place. It deepens and matures over several days. At the scale of the continent, the shape of the land influences how this air spreads. Mountain ranges can redirect air currents, while broad interior plains allow heat to extend over large connected distances. Dry regions in the southwest often become powerful source areas for hot air, especially when strong summer sunlight acts on bare ground and sparse vegetation. This very warm air can then expand eastward or northward depending on the large-scale pattern. The result is not a narrow ribbon of heat but a broad atmospheric field that covers multiple states at once. Weather maps during such periods often show unusually high values at levels well above the surface. These measurements indicate that the atmospheric column is warmer and thicker than normal. Warm air expands, so the vertical distance between pressure levels becomes greater. Meteorologists use these changes to identify intense heat patterns. A thick, warm column is a sign that the heat extends through depth and is not confined to a shallow surface layer that a passing breeze might quickly disrupt. This deep warmth changes the character of the entire lower atmosphere. Morning air begins the day from a higher starting point. The land has less work to do before afternoon temperatures reach dangerous levels. Even before midday, the atmosphere already contains stored heat from the previous day. The sun then adds more, and the rise becomes rapid. In this way, each day builds from the remains of the one before. Heat is not simply arriving anew every morning. Much of it is being carried forward. Cloud development also changes under these conditions. Rising air normally cools as it expands, and if enough moisture is present, clouds can form. But when the middle layers of the atmosphere are unusually warm, rising surface air may lose its upward drive before reaching the level needed for sustained cloud growth. This makes the atmosphere more stable. Small clouds may appear and fade, but widespread deep clouds become less common. The open sky allows more sunlight to reach the land. And the cycle continues. Observations indicate that large heat events in the United States are often associated with this combination of deep warm air and persistent upper-level high pressure. It remains uncertain how much any single event depends on distant influences such as ocean temperature patterns or shifts in the jet stream, because each event has its own structure. Yet the broad physical process is well understood. A continent under strong summer sunlight warms the air above it, and when large-scale circulation supports sinking, stable conditions, that air mass can intensify and remain in place. At this regional height, the atmosphere appears calm, though it is carrying immense energy. There may be wind at times, but the wind often moves within the warm air mass rather than replacing it. The warmth settles over the land not as a single dramatic moment, but as a sustained occupation of the lower sky. The air over fields, highways, towns, reservoirs, and forests becomes part of one connected volume, held in a state of unusual heat. This is still an outer region of the story, though it has moved inward from the planetary scale into the atmosphere over the continent itself. The focus remains on the broad body of air resting above the United States, warming in depth, descending in places, and persisting across distance. It is the heated envelope around the land, the large invisible structure within which later details will unfold. For now, the process remains atmospheric and expansive. The continent lies beneath a growing mass of warm air, and that mass continues to thicken, settle, and hold. The high-pressure lid settles over the heated region as a broad structure of atmospheric weight and motion. At the surface, pressure is simply the weight of the air above pressing downward, higher in the atmosphere. Pressure patterns describe the shape of moving air and the depth of warm or cool layers. In a heat wave, this pattern often takes the form of a strong high-pressure system that extends through a large part of the troposphere. It does not appear as a visible dome in the sky. It is an arrangement of air, pressure, and temperature that influences what the atmosphere can and cannot do. Under high pressure, air tends to sink. This descent is usually gradual, spread across a wide region rather than confined to a narrow column. As the air sinks, it enters levels of greater pressure. The air parcel is compressed, and its temperature rises. This warming is not caused by sunlight directly, though sunlight continues to warm the surface below. It comes from the basic physics of a gas being pushed into a smaller volume. The process makes the descending air warmer and drier in relative terms, reducing the chance that clouds will form. This sinking motion creates the lid-like effect, In ordinary summer conditions, heated air near the ground rises through convection, mixes upward, and may build clouds or storms if moisture and instability are sufficient. Under a strong high-pressure system, the middle atmosphere becomes warm enough to resist that upward motion. Rising air from the surface encounters a layer above that is already warm, and because the surrounding air is not cooling quickly with height, the rising parcels lose their buoyancy, their ascent weakens, the atmosphere becomes stable. Stability in this sense means resistance to vertical motion. It does not mean stillness in the everyday sense. Winds can still blow, and air continues to move horizontally, but the atmosphere no longer encourages strong upward exchange. The vertical pathway narrows. Heat near the ground is less able to disperse into higher levels, and moisture has more difficulty gathering into deep clouds. The result is a sky that often remains open, and a surface that continues to receive strong sunlight day after day. Across the United States, such a lid can stretch over many states at once. Weather maps show a broad bulge in the atmosphere, where pressure surfaces sit higher than normal because the air column beneath them is warm and expanded. The high-pressure region can remain nearly stationary for several days or longer, depending on the surrounding flow. When this happens, fronts that might otherwise bring cloud cover, rain, or cooler air are diverted around the region. The heat wave is then not just a matter of hot air already present, it becomes a locked pattern, defended by the circulation above. The lid changes the rhythm of the day. Morning begins warm because the previous day's heat has not fully escaped overnight. As the sun climbs, the land heats quickly under clear skies. Warm air rises from the ground in rippling currents, but that rise is shallow compared with what might happen in a more unstable atmosphere. The lifted air meets resistance aloft and spreads sideways or sinks again. Cloud growth stalls early. Afternoon temperatures continue to climb because the heating source remains strong, while the release mechanisms remain weak. Rainfall also becomes less likely under a persistent high-pressure lid. Rain in summer often depends on rising air that cools, condenses water vapor, and builds clouds deep enough to produce showers or storms. When sinking motion dominates the broader pattern, that chain is interrupted. Existing clouds may thin or vanish. New clouds struggle to mature. Soil then receives less moisture. Vegetation loses water, and the surface becomes more favorable to further heating. Even without moving inward to the land itself, the atmospheric lid is already shaping the region below by denying it relief. The clear sky that accompanies this setup has a double effect. During the day, it allows abundant solar energy to reach the surface. At night, a clear sky can in some cases help heat escape to space more efficiently. Yet under a deep, warm air mass, especially one rich in stored daytime energy, nighttime cooling may still be limited. The atmosphere near the surface begins the night from a high temperature, and the warm layers above reduce the overall contrast needed for faster cooling. The result is a pattern in which both day and night drift upward. The structure of the lid is not perfectly uniform. It can strengthen in some areas and weaken in others. Small disturbances may pass along its outer edges. Mountain ranges may locally influence airflow. Moisture from distant sources may briefly modify the lower atmosphere. But within the main body of the high-pressure system, the governing feature remains the same. Air is descending on the larger scale, warming through compression, and suppressing the vertical motions that could otherwise disrupt the heat. Meteorologists identify these events by studying pressure fields, temperature layers, and the height of specific atmospheric levels. They often find that extreme heat corresponds to unusually strong ridges, which are northward bulges in the pattern of upper-level flow. A ridge is not a wall but a broad arch in the atmosphere where warmer air dominates. This ridge guides wind patterns around it and often supports the persistent sinking motion linked to heat waves. When a ridge intensifies and remains fixed, it becomes the atmospheric framework for prolonged heat. Observations indicate that some of the most severe heat events occur when this high-pressure pattern resists change for many days. Instead of shifting eastward as weather systems often do, it lingers. Each additional day under the lid adds more heat to the land and the lower atmosphere. The event deepens through repetition. The heat does not need to become dramatically hotter each day to become more dangerous. Persistence alone can make it severe, because the system lacks recovery time. It remains uncertain in individual cases why one high-pressure system breaks down quickly while another holds. The answer can depend on distant wave patterns in the atmosphere, interactions with other pressure systems, and the distribution of heat across land and ocean. Yet the immediate mechanism is clear. Once the lid is in place, it favours its own continuation. Fewer clouds mean more sunlight. More sunlight means warmer ground. Warmer ground supports stronger heating of the lower air. The high-pressure structure then continues to preside over an atmosphere that is becoming steadily more prepared for further heat. From the ground, the lid is invisible. There's no edge to point toward, no surface in the sky to mark its presence. It reveals itself through absence fewer clouds, fewer storms, fewer breaks in the heat. It reveals itself through repetition, another hot morning, another bright afternoon, another night that cools too little. Above the continent, the high-pressure system remains broad and calm in appearance, but its effect is decisive. It acts as the controlling layer of the heat wave at this stage, holding the atmosphere in a state that resists relief and invites continuation. This region of the story remains overhead. It concerns the immediate atmospheric structure above the heated land, the lid that forms through sinking air and compressed warmth. The heat wave now has a governing shape. It is no longer only a warm continent beneath the summer sun. It is a continent covered by a stable, suppressing layer of high pressure that holds heat near the surface and limits the ordinary motions that might carry it away. Under the high-pressure lid, the sky opens and remains open across long stretches of the day. This is the region of the heat wave defined not by the weight of the air above, but by what disappears from view within it. Clouds become scarce. Rain-bearing towers fail to rise. Thin streaks of moisture at high altitude may drift through, but broad cover is often absent. The sunlight falls with little interruption from morning until late afternoon, and the land beneath receives it hour after hour. In this clear and repeating sky, the heat wave begins to intensify through exposure. Clouds matter because they regulate the exchange of energy between sun, air, and ground. A bright cloud deck can reflect a large fraction of incoming solar radiation back towards space. Even scattered clouds can create intervals of shade, reducing the amount of energy absorbed at the surface. When clouds are absent, this reflective barrier weakens. More sunlight reaches roads, rooftops, open soil, dry grass, riverbanks, rail lines, and walls of stone and concrete. Surfaces begin warming early in the day and continue warming without interruption. The effect is cumulative rather than sudden. A single clear day in summer is ordinary across much of the United States. A series of clear days under a persistent high-pressure system is different. Each day begins with the surface already carrying stored warmth from the one before. The sun rises over ground that has not fully recovered from the previous afternoon. Because there are few clouds to interrupt heating, the land returns quickly to high temperature. Then it continues climbing. The repeated absence of shade becomes one of the most powerful features of the event. At this stage, the atmosphere above remains stable enough to limit deep cloud growth. Small currents of warm air rise from the surface as the day advances. This process is familiar over any heated landscape. Air nearest the ground becomes warmer and lighter, then starts to lift. In an atmosphere with sufficient instability, such rising air can continue upward, cool, and condense into puffy clouds that may later grow into showers or storms. Under the heat wave sky, that growth often stalls. The rising air reaches a warmer layer aloft and loses the force needed to continue. The clouds that might have formed remain shallow, brief, or absent. This matters because afternoon storms often provide several forms of relief at once. They bring shade before rain arrives. They transport heat upward through vigorous vertical motion. They may produce downdrafts of cooler air. They wet the land and leave behind moisture that supports later evaporation. When those storms fail to appear, the daily heating cycle runs with fewer interruptions. The day becomes simpler in structure and harsher in result. Sunlight enters, surfaces absorb it, and temperatures rise. Across regional landscapes, the visual character of such a sky becomes familiar during severe heat. The blue remains broad and nearly uninterrupted. The horizon may look pale or slightly milky, where heat and fine particles accumulate in the lower atmosphere. But overhead the sky often stays stark and exposed. The brightness itself becomes part of the event. Light falls hard on every open surface. Shadows shorten toward midday and offer only narrow relief. The sky no longer behaves as a changing roof above the land. It behaves as an open passage through which solar energy arrives steadily. The clear sky effect also extends the period of daytime heating. Clouds can arrive at any hour and limit the build-up of temperature. In their absence, the warming period lasts longer. Early sunlight begins work on the surface soon after sunrise. By late morning, the rate of heating is already strong. In the afternoon, when the sun is still high and the accumulated warmth is greatest, there may still be no cloud cover to moderate it. The highest temperatures of the day are therefore reached not only because of the sun's angle, but because the entire day has remained available for heating. Meteorologists sometimes describe this as enhanced insolation, meaning increased receipt of solar radiation at the surface. The term refers to incoming sunlight, especially when little is lost to reflection by clouds. In a heat wave, enhanced insolation does not act alone. It works together with the high pressure pattern, the deep warm air mass, and the lack of widespread rain. But within this region of the story, the role of the cloudless sky is direct and clear. It removes one of the atmosphere's main moderating influences and allows the surface to absorb more energy over repeated days. The absence of clouds also changes perception at ground level. Landscapes appear sharper in the dry brightness of the afternoon. Distant objects shimmer as heated air bends light above roads and fields. Surfaces bleach under intense illumination. Grass dulls. Dark roofs radiate visible waves of distortion. Yet these are not separate events. They are surface signs of the same clear sky energy balance playing out across the region. The heat wave is not only measured by thermometers, it is also seen in the unbroken continuity of sunlit hours. At regional scale, one important consequence is that neighbouring areas can warm together. If clouds or storms formed regularly, they would break the landscape into cooler and hotter zones through shade and rainfall. During a persistent heat event, this patchwork weakens. Vast areas receive nearly continuous sunlight at the same time. Local differences remain, but the broader pattern becomes one of shared exposure. Plains, valleys, suburbs, industrial districts, croplands, and dry open terrain all spend the day under the same radiant load. Observations indicate that major heat events in the United States often feature a marked reduction in daytime cloud cover over the hottest areas. Satellite imagery during such periods commonly shows broad, clear regions coinciding with high surface temperatures. It remains uncertain in some cases how much local haze or smoke may alter the exact amount of solar energy reaching the ground, because particles in the air can both reflect and absorb radiation. Yet where skies remain largely free of deep cloud, the net daytime effect usually favors continued surface heating. The lack of clouds does not mean the atmosphere is empty of all moisture or motion. Water vapor may still be present, especially in eastern or southern parts of the country. Thin upper-level features may pass overhead, but none of these produce the kind of sustained shading needed to interrupt the heat. The important fact in this region is not absolute emptiness. It is the failure of the sky to provide relief. The normal summer cycle of cloud growth weakens, and the sun gains uninterrupted access to the land below. Through repetition, the sky itself becomes part of the heat wave's persistence. Morning after morning, the same pattern resumes. The eastern horizon brightens, light spreads quickly. By midday, the ground has absorbed several hours of direct radiation. By afternoon, temperatures press higher. Evening arrives, with surfaces still carrying large stores of heat. Then night passes with only partial release, and the next clear day begins. The sequence is simple, almost spare in its structure, but very effective in its outcome. This region remains in the open air between the high-pressure lid and the land. It is the domain of missing clouds, failed storms, and repeated sunlight. No deeper mechanisms have yet entered the frame. The focus stays on the sky as it appears and behaves during the heat wave, broad, exposed, stable, and unwilling to intervene. Across the heated region of the United States, the open sky continues to deliver energy with little pause, and the land beneath continues to receive it. Beneath the open sky, the ground begins to tell its own part of the heatwave story. The land surface is not uniform. It includes dark soil, pale dust, dry grass, crops at different stages of growth, exposed rock, leaf cover, and patches of bare earth between roots and stems. Each of these materials receives sunlight and responds according to its structure, color, moisture, and texture. Yet when a severe heat event persists, one change becomes especially important across many of these surfaces. Moisture declines, the ground dries. As that drying advances, one of the land's most effective cooling processes begins to weaken. When water is present in soil or on leaves, part of the sun's energy goes into moving that water into the air as vapor. This process is evaporation from soil and water surfaces and transpiration from plants. Together they are often described as evapotranspiration, meaning the transfer of water from land and vegetation into the atmosphere. This transfer consumes energy, instead of heating the ground directly. Some incoming solar radiation is used to change liquid water into water vapor. In practical terms, moisture acts as a cooling pathway. It does not stop the surface from warming, but it slows the rate at which sunlight becomes sensible heat, the heat that raises temperature in the air and on the land. As soils lose moisture, that pathway narrows. Less water is available to evaporate. Plants, if they are stressed, may partly close the tiny pores on their leaves that normally allow water vapor to escape. These pores are called stomata. They help regulate gas exchange and water loss. Under dry conditions, many plants reduce this outward flow in order to conserve water. The landscape then shifts in its energy balance. More of the sunlight falling on the surface is converted directly into heat rather than into evaporation. The ground grows hotter, and the air touching it warms more quickly. This transition can be gradual and difficult to notice at first. A field may still appear green in places. Shrubs may remain upright. Trees may continue to cast full shadows. Yet beneath the surface, the amount of available water may already be falling. The upper soil layers dry first, especially under repeated clear skies and high daytime temperatures. Wind can increase the loss by carrying away moist air near the surface and allowing more evaporation to continue. If little rain arrives and nighttime recovery is weak, the drying extends downward. Over time, the land becomes less able to buffer the heat. In a moist landscape, solar energy arriving at the surface is divided among several pathways. Some is reflected, some warms the ground, some warms the air, some drives evaporation. During a heat wave over drying land, the share devoted to evaporation decreases. More of the energy is redirected into heating the surface and the near-surface air. This is one reason why dry heat can intensify so rapidly after rainless periods. The land is no longer spending as much of the day moving water. It is increasingly spending the day becoming hotter. Across parts of the United States, this pattern is especially important in agricultural regions, grasslands, open rangelands, and areas that have already experienced below-average rainfall. Soil moisture there can act as a hidden control on temperature. When it is plentiful, the landscape can remain somewhat moderated even under strong sunlight. When it becomes depleted, afternoon temperatures can rise sharply. The same amount of sunlight that once supported evaporation now produces stronger heating. In this way, the heat wave is reinforced by the condition of the land itself. The effect reaches beyond bare soil. Vegetation depends on water not only for growth, but also for temperature control. A healthy plant can cool its leaves through transpiration in a way loosely comparable to sweating, though the biological mechanism is different. As water moves from roots through stems and into leaves, and then passes into the air as vapor, energy is used. The leaf surface can remain cooler than it otherwise would. When the soil dries and that flow declines, leaves warm more easily. Entire fields and tree canopies can then contribute less to local cooling. The land begins to radiate more heat back into the air. Dryness also changes the physical character of the upper soil layer. Moist soil usually conducts heat differently from dry soil, and it often has a darker, heavier coherence. Dry soil can become loose, dusty, and more vulnerable to direct heating at the surface. Thin crusts may form and crack, fine particles can separate, even where the subsurface still retains some moisture. The exposed top layer may become hot enough to make contact uncomfortable within seconds. This surface heating helps create very steep temperature differences between the ground and the air just above it, driving turbulent mixing in the lowest atmosphere. Measurements from satellites and land stations often show that surface temperatures over dry ground can become much higher than the air temperature measured at standard shelter height. A thermometer in a shaded instrument screen may record a very high value, yet the skin temperature of the sunlit ground itself can be higher still. This difference matters because the ground is the immediate source from which heat moves into the lowest air. When the surface is intensely hot and dry, it feeds the atmosphere above with steady thermal energy throughout the day. The drying of land can also sustain the heat wave from one day to the next. If rain were to fall, some solar energy on later days would again be diverted into evaporation. But under persistent high pressure, rainfall is often sparse or absent. The soil then does not recharge. Each hot day tends to make the next day easier to heat. This land-atmosphere feedback, meaning a two-way reinforcing interaction between ground conditions and the air above, is well supported by observation and modelling. Dry soil helps produce hotter air, and hotter air helps dry the soil further. The loop can continue until weather patterns change. It remains uncertain in any exact location how much of an extreme temperature outcome is controlled by soil moisture alone, because winds, humidity, vegetation type, and cloud conditions also matter. Yet the underlying principle is clear. Where the surface loses water and cannot replace it, more of the sun's energy remains available to heat the land directly. The missing moisture is not only an absence in the ground, it is an absence in the day's energy pathway. The heat wave grows harsher because one route for cooling has faded. Seen across a dry afternoon, this process is quiet and unspectacular in form. There is no single moment when the land announces that it has crossed from moist to heat amplifying. The change reveals itself through texture and persistence. Lawns pale, crop leaves curl slightly, soil hardens, dust lingers after movement, shallow ponds retreat from their edges. The air above fields and vacant lots begins to shimmer more strongly. These signs all point to the same physical shift. Water is leaving the surface system, and heat is taking a larger share of the sunlight that remains. This region of the story stays close to the ground but remains outside the built environment and outside the body. It concerns the land as living and drying material, the soil and vegetation layer that mediates between sunlight and air. Under the clear sky of the heat wave, the ground is no longer simply receiving heat. It is losing its ability to spend energy on cooling. In that loss, the surface becomes a more efficient producer of high temperature, and the air resting over it continues to warm. Across the American interior, the shape of the land begins to matter in a more direct way. The heat wave is no longer only a matter of sunlight, broad air masses, clear skies, and drying soil. It now moves through terrain, plains, plateaus, deserts, mountain slopes, and long open basins influence how heat is distributed, how air travels, and where the hottest conditions concentrate. The United States contains an unusual variety of landscapes across a large continuous span of land. And during severe heat, this variety does not cancel the danger. Instead, it helps organize the pathways along which hot air deepens and spreads. The broad plains in the center of the continent form one of the most important of these pathways. From the southern interior northward, the land remains open across great distances, with relatively few topographic barriers compared with mountain regions. Air can move across this open terrain with less interruption. When very warm and dry air develops over the southern and southwestern interior, these plains provide a corridor through which that heat can extend. The movement is not always fast. Sometimes it is gradual, supported by the larger pressure pattern rather than by a single dramatic wind event. Yet the openness of the terrain allows warm air masses to remain connected over long distances. To the west and southwest, deserts and semi-arid lands play a special role in the structure of American heat. These regions receive intense summer sunlight and often contain sparse vegetation, exposed mineral soil, and rocky surfaces with limited moisture. Because little energy is spent on evaporation compared with wetter regions, a large share of incoming radiation becomes direct heat. Afternoon surface temperatures rise sharply. The air overlying these landscapes becomes extremely warm and often very dry. This does not mean that all heat waves begin there, but such regions can serve as reservoirs of hot air that influence surrounding areas when larger weather patterns permit. Plateaus and elevated basins add another layer to the process. High ground receives strong sunlight under thinner air, and many interior plateaus remain dry for much of the warm season. The daily temperature range can be large, yet during a prolonged heat event, the repeated daytime heating still produces substantial accumulated warmth. Air descending from higher terrain into lower valleys and plains can warm further through compression. This is especially noticeable where regional wind patterns carry air downslope. A descending air parcel enters denser, lower altitude air and becomes warmer without needing additional solar heating during that descent. Thus, terrain can shape not only where the heat begins, but also how it intensifies in motion. Mountain ranges influence the flow by redirecting air and dividing moisture sources. The western United States includes long chains and elevated barriers that shape regional climate throughout the year. During heat events, these mountains can shield interior regions from marine moderation, especially when larger atmospheric patterns already favor inland warming. Air from the Pacific may have less influence far inland, while hot continental air remains dominant east of the barriers. At the same time, mountain slopes exposed to strong sunlight can heat the adjacent air, and enclosed valleys can trap warmth during the day. Valleys deserve special attention because they are places where air and heat can gather. In a broad valley under clear skies, sunlight warms the floor and sidewalls for many hours. The surrounding terrain can restrict horizontal exchange with cooler air, particularly when the larger atmospheric pattern is already stable. During the day, heated air rises from valley surfaces, but under a persistent heat event the whole local air mass may remain warm enough that relief is limited at night. Some valleys cool efficiently under ordinary dry conditions, but prolonged regional heat can reduce that cooling, especially when the air mass overhead remains warm and winds stay light. The valley then becomes a pocket where heat lingers. The Great Plains illustrate another important interaction between terrain and heat. Their openness allows not only the spread of hot air, but also the mixing of air masses from different source regions. Warm, dry air from the southwest, moisture from the Gulf of Mexico, and air from higher latitudes may all interact there. During the stage of the heat wave described here, the key point is that the plains do not block heat. They permit broad regional continuity. A mass of hot air can occupy a very large area without being broken into isolated pockets by rugged terrain. This helps heat waves in the central United States become geographically extensive. Winds near the ground also respond to temperature differences shaped by terrain. Heated surfaces produce rising motion, and cooler nearby areas may feed compensating flow toward them. On mountain slopes, upslope winds often develop during the day as warm air rises along the terrain. At night, cooler air may drain downslope. During a major heat wave, these familiar local circulations continue, but they operate within a warmer background state. The air being moved is already hotter than usual. The result is not relief, but redistribution of heat from one part of the landscape to another. Desert winds, in particular, can carry intense heat outward from source regions. When air crosses very hot, dry surfaces, it can gain temperature and lose relative humidity. If the broader pressure pattern steers that air toward populated or agricultural regions, temperatures there can rise rapidly. Such transport does not need to involve dramatic storms or visible fronts. It may occur as a steady movement within the existing hot air mass. Observations across the American West and Southwest often show episodes in which extreme inland heat is linked to air trajectories passing over arid terrain. Topography also affects how long heat remains in place. Rugged terrain can isolate communities and ecosystems from quick changes in air mass, especially when the large-scale atmosphere is stagnant. A coastal influence may cool one narrow strip of land while an inland basin only a short distance away remains much hotter. A mountain crest may separate regions experiencing the same heat wave in different forms, one dry and severe, another hot and humid, yet all remain part of the broader event. organised by the land's uneven surface and by the routes that air can follow across it. It remains uncertain in a given heatwave exactly how much each terrain feature contributes to the final temperature reached at a specific location, because cloud cover, soil moisture, vegetation, and regional wind timing all interact. Still, the governing principle is well known. Landforms shape airflow, sunlight exposure, moisture access, and the retention or export of heat. The American landscape, with its long open centre, dry southwest, interior basins, and blocking western mountains, offers many ways for heat to strengthen and spread rather than quickly disperse. Seen from above, the terrain organises the event into connected zones. Dry plateaus feed hot air into adjoining plains, valleys collect it, open grasslands allow it to travel, mountain barriers redirect it and sometimes hold it inland. Desert surfaces intensify it. None of these regions acts alone. Together they create a network of pathways through which heat moves as part of a continental system. The atmosphere follows the shape of the ground more than it appears to from a casual glance at the sky. This region of the story remains outside cities and outside the human body. It is still environmental, but now more detailed than the earlier broad land surface. The focus is on the shape of the country itself, and on the ways terrain guides the movement and concentration of hot air. Under the persistent heat wave, plains, deserts, valleys, and slopes become channels and chambers of warmth. The land does not merely endure the event, it helps steer it, deepen it, and carry it onward across the interior of the United States. Within the broader heat wave, the built landscape begins to stand apart from the surrounding land. A city is not only a collection of people and streets, it is a surface system made of stone, brick, concrete, asphalt, steel, glass, roofing material, pipes, vehicles, and narrow strips of altered soil. These materials differ sharply from forests, wetlands, cropland, or open grassland. They absorb sunlight in different ways, store energy differently, and release it on a different schedule. Under severe summer heat, the city becomes its own thermal environment, layered inside the regional event yet behaving with a distinct physical logic. This is the urban heat island, a place where temperatures are often higher than in nearby rural areas because the built surface captures and retains more heat. The term heat island does not describe a visible island with a fixed boundary. It describes a pattern observed again and again in measurements from cities around the world. Urban areas tend to remain warmer, especially after sunset and during the night, because their materials and form alter the balance of radiation, airflow, shade, and moisture. During a major heat wave, this difference can become especially important. The city receives the same broad high-pressure pattern, the same clear sky, and the same strong sunlight as the region around it, but the response of its surfaces is more intense and more persistent. Asphalt is one of the most important materials in this transformation. It covers roads, parking areas, rooftops, and paved yards. It is often dark, which means it reflects relatively little of the sun's energy and absorbs a great deal of it instead. Concrete also absorbs and stores heat, though its exact behaviour depends on composition, colour, thickness, and exposure. Brick walls, dark roofs, and stone surfaces add to this reservoir throughout the day. These materials take in solar radiation and warm not only at the surface but also within their mass. A grassy field may heat strongly in sunlight, yet it also cools through evaporation if moisture is present. A paved surface offers little such relief. Much of the energy remains as stored heat. Buildings increase the effect by adding vertical surfaces to the city's thermal structure. Sunlight does not strike only the ground. It also hits walls, windows, metal facades, and roofs from changing angles throughout the day. Some surfaces reflect light onto nearby ones. Others absorb it and later emit infrared radiation back into the urban canyon, the narrow space formed between rows of buildings. In dense districts, streets become channels where heat is exchanged repeatedly among walls, pavement, vehicles, and the lower atmosphere. This repeated exchange reduces the ability of the city to cool quickly, even when direct sunlight begins to fade. The shape of the city also alters airflow. In open countryside, wind can move more freely over fields, low vegetation, and wide horizontal surfaces. In urban areas, buildings interrupt the wind, redirect it, slow it, and create zones of turbulence mixed with pockets of stagnation. This can have mixed effects on local ventilation. In some places, air is stirred and heated, air is carried upward. In others, heat becomes trapped in enclosed streets or courtyards. What matters at this stage is that the city does not allow air to move in the same simple way as open land. The geometry of the built environment changes how warmth is distributed and how slowly it disperses. Another important difference is the loss of vegetation and exposed moist soil. Parks, trees, and planted areas remain important within cities, but they are often fragmented and limited compared with the total area covered by hard surfaces. Where vegetation is sparse, evapotranspiration declines. Less solar energy is spent moving water from ground and leaves into the air. More is converted directly into heat. A tree-lined street may be noticeably cooler than an open parking lot nearby because leaves intercept sunlight and transpire water. But when entire districts are dominated by roofs, pavement, and sealed surfaces, this cooling influence becomes too small to counter the larger thermal load. Urban materials also tend to have significant thermal inertia, meaning they resist rapid changes in temperature because of the amount of energy they can store. During the day, this property slows some of the immediate rise in surface temperature within deeper layers of walls and pavement, but it creates an important consequence later. The stored energy is released gradually after sunset. Long after the sun has gone down, concrete, brick, and asphalt continue giving heat back to the surrounding air. The city thus remains warm even when the direct source of solar radiation has ended. During a severe heat wave, this delayed release can turn night into an extension of the day's stress. Vehicles, machinery, air conditioning systems, and industrial activity add further heat to the city. This is called anthropogenic heat, meaning heat produced by human activity. Engines release it directly through combustion. Electrical systems, cooling equipment, and industrial processes release it as a byproduct. Air conditioners remove heat from indoor spaces but expel that heat outdoors. During extreme heat, when demand for cooling rises, this expelled heat increases in many neighborhoods at once. It usually does not rival the sun as the main energy source, but in dense urban areas it adds to the background burden and can raise local temperatures further, especially at night. Measurements consistently show that urban neighborhoods can differ from one another as well. Areas with mature trees, reflective roofs, lighter paving, wider spacing between buildings, and access to open green space often remain somewhat cooler than districts dominated by dark surfaces and dense construction. Industrial areas, transport corridors, warehouse zones, and neighborhoods with limited vegetation may experience stronger heat retention. The heat island is therefore not uniform. It is a mosaic shaped by design, materials, land use, and access to shade. Yet across this variation, the general principle holds: the city stores more heat and releases it more slowly than the countryside around it. During a regional heat wave, this urban effect compounds the larger atmospheric pattern. The high-pressure system maintains clear skies. The cloudless day sends strong sunlight onto rooftops and pavement. Dry surfaces allow little evaporative relief. The built mass of the city absorbs energy from sunrise until evening. Then, as regional air temperatures remain high, the city begins releasing its stored heat into an atmosphere that is already too warm. The difference between city and countryside may widen most clearly after sunset, but the city's altered energy balance is active throughout the day. It remains uncertain at the scale of one street or one block exactly how much any single material or design feature contributes to measured air temperature, because shade, wind, building height, traffic, and vegetation all interact. Yet the scientific basis for the urban heat island is strong and well established. Cities modify radiation, airflow, moisture, and heat storage in ways that make them warmer than nearby less developed landscapes. Under extreme summer conditions, these differences become not only measurable but physically consequential. This region of the story lies deeper inside the heat wave than the dry plains and open valleys. The focus now rests on the built surface itself, on streets and structures that receive sunlight, hold it, and return it slowly to the air. The city does not merely sit inside the heat event, it reshapes it at close range. Concrete, asphalt, walls, roofs, machines, and limited vegetation turn urban space into a reservoir of warmth. In that reservoir, the day's heat does not simply pass through, it lingers, accumulates, and waits for the night. Night arrives over the heated landscape without bringing the cooling that once defined the end of a summer day. The sun drops below the horizon, shadows lengthen, and direct solar radiation ceases. Yet the atmosphere does not loosen its hold. In a severe heat wave, especially one extended across cities, plains, and dry ground, darkness no longer guarantees relief. The warmth stored through the day remains in roads, walls, soil, rooftops, and the lower air itself. The ordinary pattern of evening recovery weakens. What should have been a period of release becomes instead a continuation of strain in a quieter form. This is the region of the heat wave where night loses its familiar role. Under more moderate conditions, the ground begins cooling soon after sunset by emitting infrared radiation upward. Without sunlight arriving to replace that energy, temperatures near the surface usually fall through the evening and continue declining toward dawn. The air in contact with the cooling ground also becomes cooler in rural places with clear skies and light winds. This nocturnal cooling can be strong. Fields, open soil, and low vegetation often lose heat efficiently, and the cooler air settles near the ground. Morning then begins from a relatively low temperature, allowing the next day to start with some reserve against the afternoon heat. During an extreme heat event, several factors interfere with this process. The first is simple accumulation. The day begins hot, grows hotter, and ends with an unusually large store of thermal energy spread across the surface and lower atmosphere. When sunset arrives, the system is trying to cool not from ordinary summer warmth, but from a much higher starting point. Even if the rate of cooling were normal, the night might still end with temperatures well above average. In practice, the rate itself is often reduced. The result is a night that remains abnormally warm from beginning to end. The deep warm air mass above the surface plays an important role. A hot day under persistent high pressure does not create warmth only at ground level. The lower and middle atmosphere also remain warmer than usual. This reduces the vertical contrast that helps surface heat escape efficiently. The ground is still radiating energy upward, but it is doing so beneath air that is already warm and less capable of receiving sharp cooling from below. The atmosphere near the surface becomes a shallow basin of retained heat, resting under a broader dome of warmth that has not gone away with the light. Humidity can further weaken nighttime cooling in many parts of the United States. Water vapor in the air absorbs and emits infrared radiation. When the lower atmosphere contains substantial moisture, some of the heat leaving the ground is absorbed and re-emitted back downward. The process does not stop cooling altogether, but it slows the net loss of energy to space. A humid night therefore often feels heavy not only because the air is warm, but because the normal radiative pathway of heat escape has narrowed. In a hot and humid region, darkness may bring very little temperature decline before dawn. Wind also matters, though not in a simple way. A gentle wind can sometimes help prevent heat from pooling near the ground by mixing the air. But during a regional heat wave, the air being mixed is often warm everywhere. Instead of importing coolness, the motion may simply redistribute warmth. In some places, light winds prevent the formation of a shallow, cooler layer near the surface. In others, stagnant air leaves neighborhoods wrapped in the heat stored by local surfaces. Whether calm or slightly breezy, the night remains warm because the larger air mass offers little true relief. In cities, the problem deepens. Asphalt, brick, and concrete that absorbed sunlight all day continue releasing energy for hours after sunset. Walls radiate heat into narrow streets. Pavement remains warm beneath the feet long after the sky has darkened. Rooftops slowly give back the energy they stored through the afternoon. Mechanical systems continue to expel heat outdoors. The urban heat island, already active by day, becomes especially clear at night because built materials cool more slowly than open land. A rural edge may drop several degrees while dense urban blocks remain much warmer, held in place by their own surfaces. But even outside cities, rural and semi-rural nights can fail to cool during severe heat. Dry soil that heated strongly through the day may keep warming the air above it after sunset. Grasslands with limited moisture offer little evaporative moderation. Valleys can retain warm air when the broader atmospheric pattern is too hot for normal drainage cooling to provide much benefit. Fields and orchards may spend the entire night above temperatures that once occurred only in late afternoon. The loss of nocturnal relief is therefore not only an urban condition, it becomes a regional condition when the heat wave is intense enough. This failure of cooling changes the entire daily cycle. A hot night leads directly to a hotter morning. At sunrise, the land and the lower atmosphere are already starting from an elevated baseline. There is little time in the early hours when the body, the ground, buildings, and infrastructure can shed the previous day's burden. By late morning, temperatures can already resemble what used to occur in mid-afternoon. Each day then becomes easier to heat than the one before, not only because the air mass persists, but because the night no longer resets the system. Meteorologists often pay close attention to minimum temperatures during heat events for this reason. The daily maximum shows how high the heat climbs, but the minimum shows how much relief the night provides. When minimum temperatures remain unusually high for several nights in a row, the event becomes much more dangerous. It indicates persistent heat storage in the surface and atmosphere, reduced radiative cooling, and a lack of recovery time. Observations from recent major heat waves show that elevated nighttime temperatures are often one of the clearest markers of prolonged heat stress. It remains uncertain in any one location exactly which factor dominates a specific warm night, because humidity, cloud cover, wind, terrain, soil moisture, and urban structure may all contribute in different proportions. Yet the physical outcome is unmistakable. The surface cools too little. The air stays too warm, and dawn arrives before the accumulated heat has been released. The night becomes compressed, not in duration, but in function. It is still dark, still quieter, still without direct sunlight, yet it no longer serves as the cool half of the day. Seen from the ground, this altered night is marked by small persistent signs. Walls continue to radiate warmth. Indoor spaces without sufficient cooling remain heavy and still. Pavement gives back heat through the soles of shoes. Air that should feel gentler after sunset remains thick and warm against the skin. By midnight, by the early hours before dawn, by the moment when the sky first begins to pale, the expected descent into coolness has not arrived. The heat is quieter than it was in the afternoon, but it has not withdrawn. This region of the story lies within the daily cycle itself. It is the inward turn from daytime heating to the failed cooling of darkness. The focus remains on the atmosphere near the ground and the surfaces that release their stored energy after sunset. Night, once the land's interval of recovery, becomes part of the heat wave's machinery. It preserves warmth, carries it forward, and hands it intact to the next day. As the heat wave moves inward from sky, ground, city, and night, the air itself reveals another layer of difficulty. Warm air can hold more water vapor than cool air. This is a basic physical property of the atmosphere, and it becomes more important as temperatures rise. Water vapor is the gaseous form of water, invisible in the air except when it later condenses into cloud, mist, or dew. During extreme heat, especially across the eastern and southern United States or in places where moisture flows inland from warm water, the atmosphere may contain large amounts of this vapor while remaining cloudless at the surface. The result is not only hot air, but heavy air. Air that carries heat together with moisture and changes the way warmth is felt, retained, and exchanged. Humidity is the common word used to describe how much water vapor is in the air. The simplest useful distinction is between the actual amount of vapor present and the percentage called relative humidity. Relative humidity describes how close the air is to saturation, meaning the point at which it can no longer hold its present vapor content without condensation occurring. Because warm air can hold more vapor than cool air, relative humidity can decrease in the afternoon, even if the total amount of water vapor remains high. This is why a day can feel both dry in percentage terms and still intensely oppressive if the air temperature is very high and the actual moisture content is large. In a severe heat event, moisture may arrive from several sources. The Gulf of Mexico is one of the most important for the United States, supplying humid air to large parts of the South, Midwest, and East when the wind pattern allows. Warm coastal waters, lakes, irrigated fields, wetlands, and transpiring vegetation can also add vapor to the lower atmosphere. Even in a heat wave dominated by clear skies, moisture can remain trapped within the lower air mass. The sky may stay bright and open overhead while the atmosphere near the ground grows increasingly moist and difficult to cool. This matters because moisture changes how heat moves. Dry air allows sweat to evaporate more readily from the skin, and that evaporation removes heat from the body. Moist air slows that process. The sweat may still form, but it does not pass into vapor as easily when the surrounding air already contains a large amount of water. The body then loses one of its main cooling routes. At the same time, the air itself feels heavier not because it is physically denser than dry air at the same temperature, but because the exchange of heat with the body becomes less efficient. The sensation of oppressive heat is rooted in this reduced ability to shed warmth. Meteorologists use several measures to describe this combined burden. One of the most familiar is the heat index, which estimates how hot conditions feel when temperature and humidity act together. The number is not a direct measurement of air temperature. It is an attempt to represent how difficult the atmosphere is for the human body to cool within it. Other measures, such as wet bulb temperature, capture related ideas using different physical principles. Wet bulb temperature refers to the lowest temperature that can be reached through evaporation alone under given atmospheric conditions. When this value rises, the potential for evaporative cooling falls. These measures differ in method, but they point toward the same truth. Moist heat is often more dangerous than dry heat at the same air temperature because it weakens the body's ability to release heat. Within the atmosphere itself, moisture also influences the way nights remain warm. Water vapor absorbs and emits infrared radiation, so a humid lower atmosphere can hold on to heat more effectively after sunset. This does not mean that every humid place is always hotter than every dry place. Dry regions can reach very high daytime temperatures because evaporation is limited and the surface heats efficiently. But when warmth and moisture combine, especially over many hours and through the night, the stress becomes more continuous. The air ceases to offer even partial support for cooling. It becomes a medium that keeps heat near the surface and around the body. Across the United States, this moist heat often forms a broad belt rather than a narrow zone. The southern states may experience long stretches of hot, humid air fed by marine moisture. Farther inland, that air can travel northward across plains and river valleys. Cities intensify the burden by adding stored heat to already moist air. Agricultural regions with irrigation can locally increase moisture near the ground. Forested and coastal areas may hold humidity even under bright skies. The details vary from place to place, but the essential pattern remains. The air becomes not only hot, but saturated with the ingredients that make heat harder to escape. The atmosphere in such conditions changes the experience of movement as well. A breeze that might bring relief in dry heat can feel limited in moist heat, because the problem is no longer only the temperature of the air moving past the skin. It is the air's reduced capacity to accept more vapor. If the surrounding atmosphere is already rich in water vapor, passing air removes sweat less efficiently. The body continues to work, but the return becomes smaller. Shade still helps because it lowers direct radiant heating, yet the underlying humidity remains. Even in shadow, the air can feel enveloping. Moisture near the ground often becomes especially pronounced during the morning and evening, when temperatures are lower and relative humidity rises. During a major heat wave, these hours might once have brought partial comfort. Instead, they can carry a different kind of burden. The temperature may no longer be climbing, but the air feels close and resistant. In this sense, humid heat stretches the day's stress beyond the hours of peak sunlight. It fills the intervals around them with a slower but equally persistent discomfort. Observations indicate that as the atmosphere warms overall, its capacity to hold water vapor increases. In many regions, this means that heat waves can occur in air masses with greater moisture content than in cooler climates of the past. It remains uncertain exactly how local patterns of soil moisture, vegetation, irrigation, ocean conditions, and circulation will combine in any single event. But the fundamental physics is well established. Higher temperatures allow the lower atmosphere to contain more water vapor, and when that vapor is present, it can amplify the physiological burden of heat. There is also a visual quietness to humid heat. It may not announce itself through dramatic signs. The sky can remain nearly empty of clouds. The landscape may look still, yet the air has changed in composition and function. It presses against the lungs with a warmth. It beads moisture on skin that cannot cool fast enough. It softens the sharp edge of dry heat and replaces it with a more enveloping pressure. Heat shimmer may still rise from roads and roofs, but the larger change is invisible. The atmosphere is carrying more water than before, and that water is altering every exchange between body, surface, and sky. This region of the story stays within the lower air, closer than weather systems and broader than any one street or field. It concerns the material quality of the atmosphere itself, the water vapor mixed through hot air, and the way that mixture changes the meaning of temperature. Heat is no longer only a number on a thermometer. It becomes a condition of air that holds more moisture, releases less relief, and narrows the path by which living bodies can cool. The heat wave moves inward here by changing the very medium that surrounds everything on the land. The air becomes warm, moist, and increasingly difficult to escape. Inside the hot and often humid air, the human body begins its steady work of self-preservation. It is built to function within a narrow internal temperature range, and much of its ordinary activity depends on keeping that range stable. Muscles generate heat as they move. Organs generate heat as they process nutrients and sustain life. Even at rest, the body is not cool. It is constantly producing warmth from within and constantly releasing that warmth outward. In mild weather, this exchange happens with little notice. During a severe heat wave, the balance becomes difficult. The environment grows so warm and sometimes so moist that the body's usual methods of shedding heat begin to fail. This is the region where external heat becomes a direct physiological burden. The body exchanges heat with its surroundings through several pathways. One is radiation, the emission of infrared energy from the skin toward cooler surfaces nearby. Another is convection, the transfer of heat to moving air. A third is conduction, the transfer of heat through direct contact with cooler materials. The most important protective pathway in extreme heat is evaporation, the conversion of sweat from liquid on the skin into water vapor in the air. Evaporation requires energy. When sweat evaporates, it removes heat from the skin and helps cool the blood flowing just beneath it. This mechanism allows the body to maintain a relatively stable internal condition, even when the surrounding air is warm. In a heat wave, each of these pathways becomes less effective. Radiation weakens when nearby surfaces are also hot, because the temperature difference between the body and its surroundings narrows. Convection weakens when the air itself approaches skin temperature. A breeze that would normally carry heat away may bring little benefit if it is moving very warm air. Conduction offers only limited help unless the body touches something cooler, which is often not available outdoors during severe heat. That leaves evaporation as the main defense. The body begins to sweat more, and blood vessels near the skin widen in a process called vasodilation, allowing more warm blood to reach the surface and release heat. This is an elegant system, but it has limits. Sweating depends on available body water, and its cooling power depends on how easily the sweat can evaporate. In hot, humid air, evaporation slows because the atmosphere already contains a large amount of water vapor. Sweat may gather and drip from the skin without providing its full cooling effect. The body continues working harder, sending more blood outward and producing more sweat. Yet the return on that effort declines. Heat then begins to accumulate faster than it can be released. The cardiovascular system bears much of this strain. When blood vessels widen near the skin, more blood is directed toward the body's surface to carry heat outward. To maintain circulation and blood pressure at the same time, the heart may need to beat faster. This is manageable for many people in modest heat, But as conditions intensify and persist, the demand rises. The body is trying to cool itself while also preserving flow to the brain, muscles, kidneys, and other organs during rest. The effort may already be substantial. During physical work or movement, internal heat production rises further, adding to the challenge. The skin becomes the visible front line of this process. It flushes as blood flow increases. Sweat forms first in a thin sheen, then more heavily across the face, chest, back, and limbs. Clothing may trap some of that moisture and restrict airflow, reducing evaporation further. Direct sunlight adds radiant heat onto the surface, especially on exposed skin and dark clothing. In shade, the radiant burden decreases. But the body is still surrounded by hot air and nearby surfaces that may remain warm from the day. The difference between comfort and distress narrows quickly when the environment ceases to support heat loss. The body also relies on behavior to protect its internal balance. It slows movement, seeks shade, drinks water, and rests during the hottest part of the day when possible. These responses reduce metabolic heat production and support the sweating system. But during a major heat wave, especially in places without reliable cooling, behavior may not fully compensate. A night that remains warm reduces recovery. A day that begins hot shortens the margin before heat stress returns. Work, travel, caregiving, and daily routines continue to generate heat within the body at the same time that the atmosphere resists taking it away. Children, older adults, pregnant people, outdoor workers, and people with chronic illness can face higher vulnerability, though the underlying physics is the same for everyone. The body's cooling system depends on circulation, hydration, evaporation, and access to lower environmental heat. When any of these are reduced, the burden grows. Some medications can also affect sweating, fluid balance, or blood pressure regulation, making it harder for the body to respond effectively. But even in healthy adults, extreme conditions can overpower the normal heat balance if exposure is intense enough or lasts long enough. Scientists often describe this as heat stress, meaning the combined burden placed on the body when environmental heat gain and internal heat production exceed the rate of heat loss. Heat stress is not yet a specific illness. It is the physiological strain that develops as the body works harder to maintain stability. At this stage, the person may still be compensating successfully. Sweating continues, circulation adjusts, thirst rises, fatigue appears. The body is spending more effort simply to remain within safe internal limits. Observations indicate that repeated days of severe heat can wear down this compensatory ability, even when the body acclimatizes, meaning it gradually improves its tolerance through adjustments in sweating efficiency and circulation. The protection is incomplete. Acclimatization can help, but it does not remove the basic limits imposed by high temperature, strong radiant heat, and elevated humidity. It remains uncertain exactly where those limits lie for each individual because age, health, hydration, workload, sleep, and prior heat exposure all matter. Yet the central fact remains clear. The body can survive heat only by releasing its internally produced warmth, plus any absorbed environmental heat. And during a major heat wave, the environment increasingly blocks that release. This inward region is quiet in appearance. A person standing still may show only a flushed face, damp skin, slower movement, and heavier breathing. Yet within the body, many systems are adjusting at once. Blood is being redirected. Sweat glands are active. The heart is working harder. Water is being lost. The skin is serving not only as a boundary with the world, but as a cooling organ trying to preserve the temperature of everything within. The success of that effort depends on a simple exchange. Heat must leave. When the outside air is too hot or too humid, the path narrows. This section remains at the boundary between the body and the atmosphere. It does not yet move into injury, organ strain, or cellular damage. Instead, it stays with the normal heat balance and the body's effort to maintain it. In the severe heat wave, that effort becomes constant and increasingly difficult. The surrounding air no longer serves as a receptive space for cooling. It becomes an opposing medium. Within that opposition, the body continues its steady work, sweating, circulating, and radiating what heat it can, trying to hold its internal order against a day that will not let go. As the body continues struggling to release heat, the strain moves inward from skin and circulation into organs, fluids, and cells. What begins as an effort to maintain balance can become a slow destabilization of the body's internal environment. Heat is not harmful only because it feels intense. It becomes dangerous when temperature regulation demands more from the body than the body can sustain. Water is lost, salts shift, blood flow is redistributed. Organs that rely on steady circulation begin receiving less margin for error. Proteins, membranes, and energy systems inside cells are asked to function in conditions that lie outside their preferred range. This is the region where prolonged heat ceases to be only an external pressure and becomes a systemic burden carried through the deepest working layers of the body. Dehydration is one of the first major steps in this inward strain. Sweating removes water from the body in order to cool it. Breathing also releases moisture, and high temperature can increase respiratory water loss. If fluid intake does not keep pace, the total volume of water in the body begins to fall. Blood plasma, the liquid part of blood, becomes reduced in volume. This makes circulation more difficult. The heart must work harder to move a smaller amount of fluid through the same network of vessels. The skin may still need high blood flow for cooling, but the organs also need reliable perfusion, meaning the steady delivery of blood. The body begins making trade-offs. Alongside water loss comes the loss of electrolytes, which are minerals such as sodium and potassium that carry electric charge in body fluids. These substances are essential for muscle contraction, nerve signaling, fluid balance, and many cellular processes. Sweat contains water plus varying amounts of these dissolved salts. When sweating is heavy and prolonged, and replacement is incomplete or unbalanced, the concentration of electrolytes in the body can shift. This may contribute to weakness, muscle cramps, dizziness, confusion, and more severe disturbances if the imbalance becomes large. Heat illness is not simply a matter of temperature, it is also a matter of chemistry. The cardiovascular system sits at the center of this growing problem. To cool the body, blood vessels near the skin remain widened. To preserve blood pressure, the heart rate rises. When dehydration reduces blood volume, the workload increases further. The heart must maintain output under conditions that are less favorable than usual. For people with underlying heart disease or reduced cardiovascular reserve, this burden can become especially dangerous. Yet even in healthy individuals, prolonged heat can produce fatigue, lightheadedness, and reduced capacity for physical activity because the circulation is being pulled between competing needs. The kidneys are particularly vulnerable during sustained heat. Their role is to filter blood, regulate fluid balance, and manage waste removal. When dehydration lowers blood volume, the kidneys receive less flow. At the same time, the body attempts to conserve water by concentrating urine and reducing fluid loss. This helps in the short term, but under persistent severe heat the reduced circulation can strain kidney tissue. Observations from heat waves and from workers exposed to repeated high temperatures show that kidney stress can rise significantly under these conditions. It remains uncertain how much repeated subclinical heat injury contributes to long-term kidney disease in every setting, but the immediate physiological burden is well recognized. A body short of water and overheated is forcing its kidneys to operate under diminished supply. The brain also depends on a tightly regulated internal environment. Changes in body temperature, fluid balance, and blood pressure can all affect mental function. Early signs of heat-related neurological strain may include slowed thinking, irritability, poor judgment, headache, or unusual fatigue. These changes matter because they can reduce a person's ability to recognize danger and respond effectively. The body may already be under significant stress while the mind becomes less able to organize the behaviors needed for protection. When heat illness worsens, confusion can deepen, coordination can fail, and consciousness may be altered. This marks a transition from compensation toward breakdown. Muscles are affected both directly and indirectly. Physical activity generates heat from within, adding to the thermal burden imposed by the environment. At the same time, dehydration and electrolyte imbalance can interfere with normal contraction. Muscle cramps in heat are one expression of this disturbance, though their exact cause can vary with workload and fluid composition. More broadly, the body under heat stress becomes less efficient. Effort feels heavier. Endurance shortens. The muscles are working in a system that is devoting increasing energy to cooling and circulation rather than performance. At the cellular level, extreme heat threatens the integrity of proteins and membranes. Proteins do much of the body's work in chemistry, and their structure depends on staying within a suitable temperature range. Cells possess protective responses, including the production of heat shock proteins that help stabilize other proteins under stress. These responses are part of the body's attempt to preserve function during elevated temperature. They are remarkable, but they are not unlimited. If core temperature rises too far or remains high too long, the risk of cellular dysfunction increases. Membranes may become more unstable, enzyme systems may operate poorly, and inflammatory pathways may become activated. Inflammation is part of the body's general response to injury and stress. In severe heat illness, this response can become widespread. The lining of blood vessels may be affected. The intestinal barrier, which normally keeps the contents of the gut separated from the bloodstream, may become more permeable under extreme physiological stress. This can allow inflammatory signals to intensify further. Researchers understand many parts of this process, though some of the exact pathways remain under study. What is clear is that severe heat can trigger a cascade that resembles other forms of systemic injury, where the body's own responses add to the burden rather than resolving it quickly. The transition from heat stress to heat exhaustion reflects this deepening systemic strain. Heat exhaustion generally involves heavy sweating, weakness, dizziness, nausea, headache, rapid pulse, and impaired ability to continue activity. The body is still trying to regulate temperature, but it is doing so under worsening internal conditions. If the process continues and core temperature rises further, heat stroke may develop. Heat stroke is a medical emergency marked by dangerous elevation of body temperature, together with dysfunction of the central nervous system. Sweating may still be present or may diminish. The defining issue is not the absence of sweat, but the failure of thermoregulation and the appearance of serious neurological impairment. Once heat stroke develops, the risk to organs rises sharply. The brain, liver, kidneys, heart, and muscles can all be injured. Blood clotting may become abnormal. Cells may die. Without rapid cooling and medical care, the condition can become fatal. This is why prolonged heat must be understood as more than discomfort. The body has robust systems for temperature control, but under exceptional environmental load those systems can be overwhelmed, and the consequences reach into the most vital structures of life. Observations indicate that prolonged exposure, high nighttime temperatures, physical exertion, humidity, and limited access to cooling all increase the likelihood of this inward progression from strain to injury. It remains uncertain exactly why some individuals deteriorate faster than others under similar conditions, because genetics, acclimatization, medications, hydration history, health status, and workload all contribute. Yet the overall pathway is consistent. Heat first challenges the body's balance, then narrows its reserves, then begins to injure the organs and cells that depend on that balance. This region of the story lies fully inside the body. The surface is no longer the main focus. The skin, sweat, and widened blood vessels remain important, but now attention rests on the consequences deeper within. Water is being lost from the circulation. Salts are shifting. The heart is working harder. The kidneys are conserving what they can. The brain is becoming vulnerable to confusion. Cells are activating emergency defenses against rising temperature in the severe heat wave. The body is no longer merely adapting to warmth. It is approaching the threshold where adaptation gives way to damage. Beyond the body, the heat wave begins to interact with other hazards that thrive in the same conditions. Among the most consequential are fire and smoke. Prolonged heat dries grasses, shrubs, leaf litter, and the upper layers of forest soil. It lowers the moisture content of dead plant material and can stress living vegetation until leaves curl, branches weaken, and fine fuels become easier to ignite. In this state, the landscape holds not only heat, but readiness. The energy of the sun and the dryness of the air have altered the chemistry and structure of combustible material across large areas. Fire risk rises not because heat alone creates flame, but because heat prepares the environment in which flame can spread rapidly once an ignition occurs. Wildfire depends on several linked factors. There must be fuel, meaning burnable vegetation or organic matter. There must be ignition, which may come from lightning, damaged power lines, machinery, vehicles, campfires, sparks from tools, or other human and natural sources. There must also be weather and terrain conditions that allow fire to grow. Heatwave conditions often favor all three parts of this system indirectly. Dry fuel becomes more available. Atmospheric instability and wind patterns can support fire behavior. Human systems under stress can produce more chances for accidental ignition. The heat wave does not guarantee fire, but it makes the landscape more vulnerable to it. Fine fuels respond first. Dry grass, pine needles, leaves, and small twigs can lose moisture quickly during hot weather. Because they are thin and exposed, they exchange moisture with the air more rapidly than large logs or deep organic layers. Under repeated heat and low humidity, these fine fuels may become flammable within a short time. Larger fuels take longer to dry, but prolonged heat waves can reduce their moisture as well. As this drying continues, fire intensity can increase because more material is available to burn and because combustion can penetrate deeper into shrubs, woody debris, and forest litter. Once a fire begins, hot conditions can strengthen its spread. Warm air lowers relative humidity during the day in many dry regions, allowing fuels to remain receptive to burning. Wind can tilt flames forward, preheat vegetation ahead of the fire, and carry embers beyond the main front. On slopes, fire may move uphill more rapidly because rising heat dries and warms the fuel above it. In valleys and canyons, airflow can become erratic. sometimes funneling flames through narrow terrain. All of these processes are known in fire science, but during a severe heat wave they occur in an environment already primed by drought, dryness, and high temperature. The smoke produced by wildfire adds another layer of burden to a population already stressed by heat. Smoke is a complex mixture of gases, water vapor, and tiny particles formed by incomplete combustion. Some of these particles are small enough to travel deep into the lungs. There they can irritate tissues, worsen asthma, aggravate heart and lung disease, and contribute to inflammation throughout the body. A person struggling to stay cool in extreme heat now has to breathe air that may itself impair breathing. The body's effort to cope becomes heavier. Heat increases the need for efficient circulation and ventilation, while smoke makes those tasks harder. This combination can be especially dangerous because the protective responses to heat and smoke can conflict. In hot weather, opening windows and increasing airflow may help reduce indoor temperature where air conditioning is absent. During a smoke event, opening windows may worsen indoor air quality. People may then face a difficult trade-off between cooler air and cleaner air. Buildings without effective filtration or cooling can become traps of different kinds, either overheating or filling with smoke. Public health responses often emphasize cooling centers and clean air shelters for this reason, but access is uneven and travel itself can be difficult during major fire events. Even when flames are far away, smoke can spread over long distances. Upper-level winds and atmospheric stability can transport it across states or entire regions. Under certain conditions, smoke settles near the ground and lingers, especially overnight or in basins where air exchange is limited. The sky may turn pale or copper-toned. Sunlight may dim slightly, but the reduction is often not enough to provide meaningful cooling at the surface. Instead, the atmosphere becomes a layered burden of warmth and contamination. People inhale the byproducts of distant burning while still enduring dangerous heat close to the ground. Heat can also influence the behavior of thunderstorms in ways that matter for fire. In some very dry environments, storms may produce lightning with little rainfall reaching the surface because raindrops evaporate in the dry lower air. This is sometimes called dry lightning. Such storms can ignite vegetation without providing enough water to suppress the new fire. Strong downdrafts from collapsing storms may then spread flames once they begin. The exact balance between storm formation and dryness varies by region and event, but observations from Western North America show that hot, dry periods often create opportunities for lightning-caused fire growth. The burden of smoke extends inward again to the body's existing heat stress. Breathing smoky air can increase heart rate and inflammation. It can reduce exercise tolerance and aggravate underlying respiratory illness. People may avoid going outside, yet indoor spaces without cooling may remain dangerously hot. Those who must work outdoors, evacuate, or protect property face both heat exposure and polluted air at once. Protective masks may reduce inhaled particles when properly designed and fitted, but they can also feel uncomfortable in intense heat and are not always available or usable for everyone. The body is asked to cool, breathe, and think clearly under increasingly compromised conditions. Infrastructure strained by heat can also contribute to fire risk. Electrical equipment may fail, power lines may sag, dry vegetation near roads and rail lines may ignite from sparks or friction. Vehicles parked on dry grass can start fires when hot exhaust systems contact fine fuel. Industrial sites and machinery operating in hot, dry conditions may face increased hazard. Here again, the heat wave acts as an amplifier rather than the only cause. It creates an environment in which small ignition sources can produce larger consequences. It remains uncertain in any one heat event exactly where the greatest fire activity will develop, because ignition timing, wind shifts, local drought history, fuel type, and human actions all matter. Yet the physical connection between prolonged heat, fuel drying, wildfire behavior, and smoke exposure is well established. A heat wave can turn landscapes more flammable and populations more vulnerable at the same time. The same weather that raises body temperature can also prepare forests, grasslands, and shrublands to burn, then fill the air with particles that make recovery harder. Seen across a broad region, the sequence is sobering in its simplicity. Heat dries vegetation. Dry vegetation burns more easily. Burning vegetation produces smoke. Smoke spreads into communities already under thermal stress. The hazard multiplies without changing its basic setting. The sky remains warm. The ground remains dry. The air becomes harder to breathe. What began as a story of temperature alone becomes a story of compound exposure, where one extreme condition feeds another and the burden on daily life thickens. This region of the story remains just outside the deepest human systems, yet it presses directly against them. Fire alters the land and smoke alters the air, creating a close environmental hazard around people already strained by heat. The heat wave now reaches beyond temperature into combustion and inhalation. It dries fuel, invites flame, and then fills the atmosphere with the residue of burning. In that residue, the body's search for relief becomes even more difficult, and the wider landscape of the event grows more dangerous still. As the heat wave presses deeper into human systems, it enters the structures that support ordinary life: electricity, water supply, roads, railways, buildings, communication networks, and public services are not separate from the atmosphere around them. They are physical systems made of materials that expand, soften, strain, overheat, and fail under sustained temperature extremes. During moderate summer warmth, these systems usually continue with manageable stress. During a severe and prolonged heat wave, the margin narrows. Demand rises just as equipment loses efficiency. Materials behave differently from the way they do in cooler weather. Infrastructure begins to reflect the same physical rule already seen in land, air, and body. Under extreme heat, energy accumulates faster than it can be safely managed. The electric grid is often among the first large systems to feel this burden. In hot weather, demand for electricity rises sharply because cooling becomes essential in homes, offices, hospitals, shops, transit systems, data centers, and water treatment facilities. Air conditioners, fans, refrigeration systems, and pumps all draw power at the same time across wide regions. The grid is designed to handle variation, but severe heat can push usage towards seasonal extremes for many hours or many days in succession. Evening no longer guarantees a strong drop in demand when nights remain warm. Instead of a daytime peak followed by substantial relief, utilities may face long high plateaus of electricity use extending through the dark hours. At the same time, the equipment carrying and transforming that electricity can perform less efficiently in the heat. Power lines warm as current passes through them. When the surrounding air is already hot, their ability to release that heat decreases. The metal expands and sags more between towers. Transformers, which shift electricity between voltages, also generate heat during operation and must shed it to their surroundings. If the surrounding environment is unusually warm, cooling becomes less effective. The same applies to many parts of the generation system, whether electricity comes from thermal plants, hydropower, wind, solar, or other sources, severe heat can reduce efficiency somewhere in the chain, even while overall demand climbs. Power plants that rely on water for cooling may face additional strain. Warm river or reservoir water is less effective as a cooling medium than cooler water, and drought can reduce supply at the same time. Water temperatures may also approach regulatory or ecological limits for discharge, because releasing overly warm water can damage downstream ecosystems. Thus, a heat wave may increase the need for electricity precisely when some generators face greater difficulty producing it. This mismatch between rising demand and reduced performance is one of the defining infrastructure features of extreme heat. Buildings themselves become part of this energy problem. A building in high heat is a thermal container receiving solar radiation through roofs, walls, and windows, while also generating internal heat from people, appliances, lighting, and machines. Insulation, reflective surfaces, ventilation, and shading can reduce the burden. But many buildings are not designed for sustained extreme temperatures or for nights that stay hot. Upper floors, poorly insulated rooms, and spaces beneath dark roofs may accumulate heat through the day and fail to release it overnight. In buildings without effective cooling, indoor temperatures can rise to levels dangerous for sleep, work, and survival. In buildings with cooling, the strain shifts outward to the power system and the outdoor air, where rejected heat adds to the urban burden. Roads and railways respond to heat through expansion and softening. Asphalt pavement can become more pliable under intense sunlight and high air temperature. Heavy traffic over softened surfaces may produce ruts, bleeding asphalt, or localized deformation. Concrete expands as it warms, and if the movement exceeds what joints can accommodate, stress may build. Rail tracks, made of steel, also expand in heat. Continuous welded rail is carefully tensioned and monitored, but under exceptional temperature conditions the risk of track misalignment rises. Rail operators may reduce train speeds in extreme heat to lower the chance of damage or derailment. Roads, runways, and tracks are engineered with thermal behavior in mind, yet severe heat can push them closer to their design limits. Vehicles and transport systems carry their own vulnerabilities. Engines, batteries, brakes, tires, and cooling systems all operate less comfortably in very hot conditions. Public transit vehicles may become dangerous if air conditioning fails. Aircraft performance can also be affected because hot air is less dense than cool air. Lower air density reduces lift and engine performance, which can limit payload under some conditions, especially at high elevation airports. The physical details vary across systems, but the general pattern remains. Heat changes the properties of materials and fluids, and transport systems must compensate through speed limits, load adjustments, inspections, or temporary service changes. Water systems face a different but equally important burden. Human demand for water often rises during heat because people drink more, bathe more, irrigate more, and use more water for cooling, agriculture, and firefighting. At the same time, evaporation from reservoirs, canals, soils, and open storage surfaces increases. Drought may already have lowered supply before the heat wave intensifies. Pipes, pumps, treatment plants, and distribution networks must continue operating under high electrical demand and hot environmental conditions. If power falters, water systems can also be affected, linking one infrastructure stress to another. In some regions, warm source water may also create challenges for water quality management by altering biological activity in reservoirs and distribution systems. Communication systems and digital infrastructure, though less visible, also depend on thermal control. Data centers, server rooms, telecommunications equipment, and signal systems generate heat continuously and rely on cooling to maintain function. During a widespread heat event, those cooling systems draw more electricity while operating against a warmer background environment. Backup systems may be tested if grid instability appears. People often think of modern communication as weightless, but it rests on hardware that obeys the same physical rules as all other machines. Heat must be moved away. When the environment grows hotter, that task becomes harder. Hospitals, emergency services, and public health networks experience a rising load as heat illness increases, air quality worsens, and vulnerable populations need transport or shelter. Ambulance calls may increase. Emergency departments may receive more patients with dehydration, cardiovascular strain, respiratory distress, kidney problems, and complications of existing disease. Cooling centers may open, requiring staffing, electricity, water, and transportation access. The social function of infrastructure becomes clearer here. These systems are not only metal, concrete, and wires, they are organized forms of care, and heat places pressure on both their physical and human components at once. Observations from past heat waves show that infrastructure failures are rarely the result of one simple breaking point. More often, they emerge from multiple stresses occurring together. A hot night sustains electricity demand. A transformer already running warm faces reduced cooling. A local outage then affects pumps, traffic signals, elevators, home medical equipment, and refrigeration. People who lose cooling indoors may need transportation to safer spaces, but transit may itself be running under heat restrictions. The event spreads across interconnected systems because those systems depend on each other in ordinary times, and even more so in extremes. It remains uncertain exactly which elements of infrastructure will fail first in any given heat wave, because design standards, maintenance, redundancy, local climate history, and timing all vary. Yet the broad scientific and engineering principle is well understood. Extreme heat alters material behavior, increases energy demand, reduces the efficiency of cooling and transmission, and exposes interdependence among systems that normally operate unnoticed. A society built for a certain thermal range becomes less reliable when that range is exceeded for long periods. This region of the story lies inside the human-made shell around daily life. The focus is no longer on the body alone or on the landscape outside, but on the systems that mediate between them. Wires hum under heavy load. Transformers shed heat into already warm air. Pipes move water through sunlit ground. Rails expand. Roads soften. Buildings trap or reject heat depending on how they are made and how power reaches them. In the severe heat wave, infrastructure reveals itself as a collection of thermal problems held together by engineering and habit. When the atmosphere grows too hot for too long, that arrangement begins to strain, and ordinary life becomes harder to sustain. After the heat has crossed sky, land, city, body, fire, and infrastructure, it reaches the level where it is named, measured, and compared. This is the inward region of instruments, records, and scientific interpretation. A heat wave is experienced through skin and landscape, yet it is also defined through thermometers, weather stations, satellites, historical archives, and statistical methods that place one event beside many others. Without measurement, extreme heat would still be real, but it would remain local and immediate. With measurement, it becomes part of a longer pattern. Scientists can determine how unusual an event is, how large an area it covers, how long it persists, how its nights compare with its days, and how likely such an event would have been in a cooler climate. This is the region where observation becomes explanation. The most familiar instrument in this work is the thermometer. Though modern meteorology depends on many kinds of sensors, air temperature is usually measured in a standard shelter that protects the instrument from direct sunlight and precipitation while allowing air to circulate around it. This matters because a thermometer placed on hot pavement or in full sun would measure the temperature of a local heated surface environment rather than the standard air temperature used for weather records. The aim is not to deny that surfaces become much hotter than the air, but to maintain a consistent reference so temperatures can be compared across places and decades. Weather stations across the United States record temperature, humidity, wind, pressure, and other variables at regular intervals. Some are located at airports, others in rural observing networks, research sites, and urban locations. Satellites add a broader view, measuring land surface temperature, cloud cover, vegetation stress, fire activity, and atmospheric structure. Weather balloons rise through the atmosphere and reveal how temperature and moisture change with height. Reanalysis systems combine many such observations with physical models to produce a coherent estimate of atmospheric conditions over time. These tools do not replace one another. They form layers of evidence, each revealing a different dimension of the heat wave. To describe an event as record-breaking or historically unusual, scientists compare current observations with a baseline period from the past. A daily maximum temperature can be compared with previous maxima for the same calendar date, month, season, or station history. A nighttime minimum can be compared the same way. Duration also matters. One isolated day of exceptional heat is different from a run of many consecutive days and nights above local thresholds. Area matters as well. A localized record at one station does not mean an entire national event is unprecedented. While a widespread period of exceptionally high temperatures across many states may signal a large-scale extreme, even if not every station breaks a record. This is where percentiles and anomalies become useful. An anomaly is the difference between an observed temperature and the average for that place and time of year. A percentile shows where an observation sits within a longer historical distribution. A value in the uppermost percentiles indicates unusual heat compared with what has typically been observed. These concepts help scientists compare places with different climates. A temperature that is ordinary in a desert may be extraordinary in a northern coastal city. Extreme heat is therefore measured not only by absolute numbers, but by deviation from local expectations and by its ability to persist. Nighttime temperatures have become especially important in recent heat analysis. A very high afternoon maximum matters greatly, but a high minimum temperature can indicate that the system is storing heat and failing to release it. Scientists therefore examine the full daily cycle rather than focusing only on the daytime peak. Some heatwave definitions require several consecutive days above a threshold. Others include nighttime minima, humidity, or local health outcomes. There is no single universal definition because the impact of heat depends on climate, acclimatization, infrastructure, and vulnerability. Still, the central scientific goal remains consistent. The event must be described in a way that captures both meteorological extremity and practical significance. Humidity complicates the measurement of danger in useful ways. Air temperature alone does not fully describe human heat stress. So meteorologists and public health agencies often use derived quantities such as the heat index or wet bulb, globe temperature, in occupational and athletic settings. These measures account for combinations of temperature, moisture, sunlight, and sometimes wind. They help identify conditions under which ordinary cooling by sweating becomes less effective. A region with lower air temperature but much higher humidity may pose comparable or greater physiological danger than a hotter but drier place. Thus, scientific measurement of heat moves from simple temperature toward a fuller description of the environment the body experiences. When scientists ask whether a heat wave is something never seen before, they proceed carefully. A phrase like that may refer to a local all-time record, the earliest occurrence of a given threshold in the season, the longest run of extremely warm nights, the largest area affected at once, or the strongest event relative to climate norms. Observations may show that one dimension is unprecedented while another is not. It remains important not to confuse rarity with uniqueness in every respect. Science often advances by separating these layers rather than blending them into one dramatic claim. A heat wave may be extraordinary because of its duration, spatial reach, nighttime warmth, moisture burden, or timing within the year even if the absolute daytime temperature is not the highest ever observed everywhere. From measurement, the analysis moves toward attribution. Event attribution is the field in which scientists estimate how human-caused climate change has influenced the probability or intensity of a particular extreme event. The basic logic is comparative. Researchers use observations and climate models to examine two worlds: the world as it exists now, shaped by greenhouse gas emissions, and a counterfactual world that represents a climate without the same human influence. They then ask how likely an event of the observed magnitude would be in each world. If the event is far more likely, or more intense, in the current climate, human influence is said to have increased its probability or severity. This does not mean that climate change is treated as the sole cause of any specific heat wave. Weather patterns still matter: high pressure, dry soil, clear skies, terrain, and circulation all remain immediate causes. Attribution addresses the background conditions within which those weather patterns operate. A useful analogy is that of loaded dice. The roll still varies, but the odds have shifted. In a warmer climate, the baseline from which heat waves develop is higher. Records are approached more easily. Thresholds are crossed sooner in the day and more often in the season. Warm nights become more common. The same type of weather pattern can now produce higher temperatures than it would have in an earlier, cooler background climate. Researchers express attribution results in careful language. They may say that climate change made an event several times more likely, or that it increased the event's intensity by a certain fraction of a degree. Sometimes the signal is very strong, especially for heat extremes, because the thermodynamic link between greenhouse warming and temperature is direct. In other cases, uncertainty is larger because observations are sparse, regional variability is high, or models differ in their representation of circulation. Heat is among the clearest classes of extremes for attribution, but even here scientists usually distinguish between what is robustly known and what remains less certain about regional details. Seen at this level, the heat wave becomes both an event and a data structure. It is still the same sunlight on pavement, the same warm nights, the same burden on the body, but now it is organized into time series, maps, anomalies, return periods, and probability ratios. The quiet work of instruments and archives reveals that what feels overwhelming in the present also belongs to a changing pattern over decades. The thermometers do not explain everything on their own, yet they make comparison possible, and comparison is what allows the event to be recognized not merely as hot, but as historically significant. This region of the story remains scientific and interpretive. It does not yet move to the deepest long-term meaning of the changing climate itself. It stays with the methods by which unusual heat is established, described, and linked to a warming world. Stations record, satellites observe, models compare one climate background with another. Through those methods, the heat wave is measured not only as weather happening now, but as an event whose rarity, severity, and shifted probability can be stated with growing confidence. At the deepest inner layer of the heat wave, the event is no longer only a matter of weather moving across a continent. It becomes part of the altered background state of the climate itself. Weather still rises and falls from day to day. High pressure still forms. Clouds still fail or grow. Dry soils still amplify heat, and cities still store warmth. Yet beneath all these immediate processes lies a slower shift in the baseline from which they now emerge. The average temperature of the planet has increased. Oceans have absorbed vast amounts of heat. Land areas have warmed. The lower atmosphere holds more energy than it once did. In that changed background, the same kinds of summertime weather patterns now operate in a warmer world. Climate is not the same as weather. Weather is the short-term state of the atmosphere, the heat of one afternoon, the persistence of one ridge of high pressure, the burden of 1 week without rain. Climate is the long-term statistical pattern within which such events occur. It is the average, the range, the frequency of extremes, and the probabilities that shape what is ordinary, rare, or unprecedented over decades. When climate warms, it does not eliminate weather variability. Cool days still occur. Storms still interrupt heat at times, but the distribution shifts. The entire field within which hot events happen moves toward higher values. This is why heat extremes are among the clearest signals of a warming world. The primary driver of this long-term warming is the increase in greenhouse gases produced by human activity, especially carbon dioxide from the burning of coal, oil, and natural gas, along with methane, nitrous oxide, and other heat-trapping gases. These gases alter the Earth's energy balance by absorbing some of the infrared radiation that the surface emits, and reducing the rate at which heat escapes to space. The process is not mysterious or sudden. It is rooted in well-established physics measured in laboratories, observed in the atmosphere, and confirmed across many lines of evidence. More greenhouse gases mean that, all else being equal, more energy remains in the climate system. That retained energy does not warm every place equally or every season in the same way. Oceans respond differently from land. High latitudes warm differently from low latitudes. Moist and dry regions differ in their feedbacks. Yet over the United States, as in much of the world, the background temperature has risen enough that heat waves now develop on top of a warmer starting point. A summer pattern that once produced a very hot event may now produce a more severe one. A threshold once reached only rarely may now be crossed more often. Nights that once cooled below a certain level may now remain above it for longer stretches. The weather pattern matters, but the baseline beneath it matters too. This shift is especially visible in the statistics of extreme heat. Observations indicate that hot extremes have increased in frequency and intensity over many land regions, while cold extremes have generally decreased. The exact pace and expression vary by region, season, and metric, but the broad pattern is robust. Heat records are being challenged in a climate that has moved upward. Event attribution studies repeatedly find that many severe heat waves have become more likely because of human-caused warming. Some events that would have been very improbable in an earlier climate now occur with much greater chance. Others, while not wholly impossible before, now arrive with higher temperatures, longer duration, or wider spatial extent. Warm nights are one of the clearest expressions of this new reality. The body, the land, and infrastructure all depend on darkness as a time of release. When the baseline climate warms, nighttime minima tend to rise along with daytime maxima. The result is not merely hotter afternoons, but reduced recovery. This has large consequences for health, agriculture, ecosystems, and energy demand. A climate that produces more frequent warm nights is a climate in which cumulative heat burden grows more readily. The event no longer has to reach astonishing daytime peaks to become dangerous. Persistence and lack of recovery are enough. Soil moisture feedbacks and drought can further intensify this climate signal. In some regions, warming increases evaporation demand, meaning the atmosphere can draw more water from soils and vegetation when moisture is available. If rainfall does not keep pace, the land may dry more quickly, and the cooling pathway of evaporation weakens. This allows more of the sun's energy to become direct heat at the surface. The cycle then reinforces itself. Climate change does not create every drought or every dry spell, but warming can intensify the thermal side of these episodes and raise the likelihood that dry conditions, once present, will be accompanied by more severe heat. Oceans also matter at this deep layer, though not in the immediate way they matter to local weather. Because the oceans store enormous amounts of excess heat, they influence the broader climate system over long periods. Warmer ocean conditions can affect atmospheric moisture, circulation patterns, and seasonal background temperatures. It remains uncertain how some regional circulation features may change in detail as warming continues, especially features involving complex jet stream behavior or long-lived blocking patterns. Scientists continue to study these questions carefully, but uncertainty about some circulation responses does not weaken the central conclusion about thermodynamics. When the climate system contains more heat, the potential for more intense heat extremes increases. The phrase "something never seen before" can therefore be understood more deeply here. It may refer not only to a broken thermometer record or an unusually long stretch of hot nights. It may also refer to the emergence of heat conditions made possible by a climate baseline that did not exist in earlier generations. This does not mean that every single event is wholly outside the natural range of past weather. Rather, it means that the probability landscape has changed enough that combinations of duration, intensity, humidity, spatial reach, and nighttime warmth now appear in forms that were once much less likely. The novelty lies as much in the pattern of recurrence as in any one number. Human societies often experience climate change through these altered extremes before they perceive it through averages. A small rise in the long-term mean may sound abstract, but a shifted mean changes the tails of the distribution, where extremes live. Because the hottest events occur at the edge of what the system can produce. Moving the background even modestly can enlarge the chance of surpassing previous limits. What was once a rare outlier becomes more common. What was once nearly unimaginable begins to enter practical planning. Infrastructure designed for an older climate faces a future with more frequent strain. Public health systems face longer heat seasons. Ecosystems face conditions that may exceed their accustomed tolerance. Adaptation can reduce some of the harm. Better urban design, more reflective surfaces, expanded tree cover, stronger buildings, resilient power systems, early warning, labour protections, cooling access, and public health planning can all save lives and reduce damage. These measures are essential, yet adaptation operates within the climate conditions that exist. If warming continues, the baseline continues to rise, and the challenge becomes greater. Mitigation. The reduction of greenhouse gas emissions addresses the deeper cause by limiting how far the background climate shifts. Adaptation manages the symptoms and near-term risks. Mitigation limits the long-term escalation. Both belong to the physical story of heat because both affect the temperatures through which future societies must live. At this innermost level, the heat wave is understood not only as an episode passing over the United States, but as a local expression of a planetary energy imbalance sustained over time. The sunlight of summer is not new. High pressure is not new. Dry soils and hot cities are not new. What has changed is the climate stage on which these familiar processes now unfold. More heat is being retained in the Earth system. More warmth is available to load the atmosphere, the land, and the night. The event draws its immediate shape from weather, but its growing intensity draws from climate. The meaning of the heat wave becomes quiet and expansive here. It is no longer just the brightness of one cloudless afternoon or the stillness of one midnight that does not cool. It is the realization that such days and nights now arise from a warmer normal. The outer layers of the event, from sunlight to air mass to city street to human skin, all depend on this inner condition. The baseline has shifted. The probabilities have changed. The margins of safety have narrowed. In that sense, the heat wave is not separate from the century around it. It is one of the clearest ways the changing climate enters ordinary life, not as theory, but as temperature carried through sky, ground, body, and time. The heat settles at last into a quieter understanding. The event has moved from the outer brightness of the summer sun to the inner workings of air, land, cities, bodies, and the climate beneath them all. At every layer, the same pattern remains. Energy arrives, lingers, and finds fewer paths away. The sky offers little shade. The ground offers less moisture. The night offers less release. The body works harder to hold its balance. Systems built for ordinary summer conditions begin to strain under a burden that lasts too long and cools too little. In this stillness, the heat wave appears less like a sudden disturbance and more like a slow occupation of the world. It rests over highways and dry fields, over rooftops and reservoirs, over forests ready to burn and rooms that cannot cool. It passes through blood and breath, through wires and pipes, through measurements written into records and through probabilities shifting across decades. Nothing in it is hurried, yet everything in it accumulates. The danger comes not only from how hot the air becomes, but from how completely the warmth enters each layer and remains there. The deeper truth is quiet. The weather event and the climate trend are not separate stories. They meet in the same afternoon, the same sleepless night, the same heated wall still giving warmth back after dark. What once seemed like the edge of expectation becomes more familiar. What once might have passed as rare now returns with greater ease. The land, the atmosphere, and the structures of daily life all reveal this change in their own steady ways. So the heat wave comes to rest not as spectacle, but as condition. A warming world expresses itself through ordinary sunlight made more dangerous by persistence, by dryness, by stored heat, and by a baseline that has risen. The silence after sunset no longer means coolness. The morning no longer begins from relief. The season itself feels altered, carrying more heat than it once did, and holding that heat for longer than before.